Welcome to our comprehensive guide on building microservices with Go programming language. In this course, we will explore service architecture design patterns and learn how to build robust, scalable microservices using Go. Microservices architecture has become the standard approach for building modern distributed systems, offering benefits like independent deployability, technology diversity, and improved fault isolation. Go, with its simplicity, excellent performance, and built-in concurrency support, is an ideal choice for microservices development. Throughout this course, we will cover four main areas. First, service architecture design principles that help you break down monolithic applications into well-defined, independent services. Second, inter-service communication patterns, including synchronous and asynchronous communication methods. Third, distributed system patterns that ensure reliability, fault tolerance, and scalability in your microservices ecosystem. Finally, practical Go implementation strategies with real-world examples and best practices. Let us begin by understanding the fundamental principles of microservices architecture. The first principle is service decomposition, which involves breaking down large, monolithic applications into smaller, independent services. Each service should have a single responsibility and be organized around business capabilities rather than technical layers. This approach ensures that services are loosely coupled and can be developed, deployed, and scaled independently. The second crucial principle is database per service pattern. Unlike monolithic applications where all components share a single database, in microservices architecture, each service owns and manages its private database. This ensures data isolation, prevents tight coupling between services, and allows each service to choose the most appropriate database technology for its specific needs. These principles form the foundation for building maintainable and scalable microservices systems. The API gateway pattern is a critical component in microservices architecture that acts as a single entry point for all client requests. Instead of clients directly communicating with multiple microservices, they send all requests to the API gateway, which then routes them to the appropriate backend services. This pattern provides several advantages. It simplifies client interactions by providing a unified interface, handles cross-cutting concerns like authentication, authorization, rate limiting, and request logging in a centralized manner, and can perform request aggregation by combining responses from multiple services into a single response. The API gateway also handles protocol translation, allowing clients to use different protocols than the backend services. In Go, implementing an API gateway can be achieved using popular routing libraries like GorillaMux or Gin. The basic implementation involves creating a router that defines different routes for different services, and then forwarding requests to the appropriate microservice endpoints. Service discovery is essential in microservices architecture because service instances can dynamically change their locations due to auto-scaling, failures, or deployments. There are two main service discovery patterns. Client-side discovery is where the client is responsible for determining the locations of available service instances and load balancing between them. The client queries a service registry, such as Console, Eureka, or etcd, to obtain the locations of service instances, then selects an available instance and makes a request. This approach gives clients full control over the load balancing algorithm, but increases complexity on the client side. Server-side discovery is where the client makes a request to a load balancer, which queries the service registry and forwards the request to an available service instance. Tools like Nginx, HAProxy, or cloud-based load balancers like AWS Elastic Load Balancer handle this process. This approach simplifies client implementation, but introduces an additional network hop and potential single point of failure. The circuit breaker pattern is inspired by electrical circuit breakers and is designed to prevent cascading failures in distributed systems. When a service starts failing, instead of continuing to make requests that will likely fail, the circuit breaker trips and prevents further calls to the failing service. This gives the failing service time to recover while protecting the calling service from being overwhelmed. The circuit breaker operates in 3 distinct states. The closed state is the normal operating mode where requests flow through normally. When the number of failures reaches a configured threshold, the circuit breaker transitions to the open state. In the open state, the circuit breaker immediately rejects requests without attempting to call the failing service, returning an error or default response. After a configured timeout period, the circuit breaker enters the half-open state, where it allows a limited number of test requests to determine if the service has recovered. If these requests succeed, the circuit breaker returns to the closed state. If they fail, it returns to the open state. Implementing a circuit breaker in Go requires defining a structure that maintains the breaker's state and configuration. The basic circuit breaker structure includes several key fields. A mutex for thread safety, since multiple Go routines might access the circuit breaker concurrently. A state field that tracks the current state as a string. A failure count that increments with each failure. A failure threshold that defines when to open the circuit. And a timeout duration that specifies how long to wait before transitioning from open to half-open state. The execute method is the core functionality that wraps the protected operation. Before executing the provided function, it checks if the circuit is in the open state. If the circuit is open, it immediately returns an error indicating the circuit is open. If the circuit is closed or half-open, it executes the function and handles the result accordingly. State management is crucial for the circuit breaker's effectiveness. The on-failure method is called whenever a protected operation fails. It increments the failure count and checks if the failure count has reached or exceeded the configured threshold. If the threshold is reached, the circuit breaker transitions to the open state and sets a reset time by adding the configured timeout to the current time. This prevents immediate attempts to call the failing service. The on-success method is called when a protected operation succeeds. It resets the failure count to 0, indicating that the service is working properly. Additionally, if the circuit breaker is currently in the half-open state, a successful operation transitions it back to the closed state, allowing normal traffic flow to resume. This state management ensures that the circuit breaker responds appropriately to both failures and recoveries. Using a circuit breaker in practice involves initializing it with appropriate configuration values and wrapping your service calls with the breaker's execute method. When creating a new circuit breaker, you specify the failure threshold and timeout duration. For example, a threshold of 3 failures and a timeout of 30 seconds means the circuit will open after 3 consecutive failures and remain open for 30 seconds before allowing test requests. To protect a service call, you wrap your external service call within an anonymous function and pass it to the execute method. The circuit breaker handles all the state management and decision-making automatically. For production use, consider using established libraries like GoBreaker by Sony, which provides a robust, well-tested implementation. GoBreaker offers additional features like configurable, ready-to-trip functions, success thresholds for half-open state, and detailed metrics. When configuring the settings, you specify the service name for identification, the timeout duration for how long the circuit stays open, and max requests, which defines how many requests are allowed in the half-open state. Proper configuration is essential for effective circuit breaker operation. The configuration includes several key parameters. Failure threshold determines how many consecutive failures trigger the circuit to open. Reset timeout specifies how long the circuit stays open before transitioning to half-open state. And max requests defines the number of requests allowed in the half-open state to test service recovery. These values should be tuned based on your specific service requirements and acceptable failure rates. Monitoring and observability are equally important for circuit breaker effectiveness. Implement comprehensive metrics collection to track circuit breaker behavior. Key metrics to monitor include the current state of each circuit breaker, failure counts and success counts over time, and state transition frequencies. The monitoring function should log essential information like the current state, number of failures, and number of successes. This data helps in troubleshooting issues, tuning configuration parameters, and understanding service health patterns. Consider integrating with monitoring systems like Prometheus and Grafana to visualize circuit breaker metrics and set up alerts for prolonged open states. Circuit breakers provide significant benefits for microservices architectures. The primary advantage is preventing cascading failures across your microservices ecosystem. When one service fails, the circuit breaker prevents the failure from propagating to dependent services, maintaining overall system stability. Circuit breakers enable graceful degradation during service outages by allowing applications to provide fallback responses or alternative functionality when a service is unavailable. They also reduce response times during failures by immediately failing fast instead of waiting for timeouts, improving user experience. Additionally, circuit breakers give failing services time to recover by reducing load, which can help services return to normal operation more quickly. However, implementing circuit breakers comes with challenges that must be carefully addressed. Threshold tuning requires careful consideration of your service's normal failure rates and acceptable downtime. Proper fallback mechanisms must be implemented to provide meaningful responses when services are unavailable. The system must correctly handle partial failures where some operations succeed while others fail. Comprehensive monitoring and alerting are essential to track circuit breaker behavior and respond to issues promptly. Following best practices ensures effective circuit breaker implementation. First, set appropriate thresholds based on your service level agreements and historical failure patterns. The threshold should be low enough to detect problems quickly, but high enough to avoid false positives from temporary glitches. Implement meaningful fallback mechanisms that provide degraded but functional service when the circuit is open. This might include returning cached data, default values, or alternative service endpoints. Use exponential backoff strategies in conjunction with circuit breakers to gradually increase retry intervals, preventing immediate overload when services recover. Always test circuit breaker behavior in staging environments that closely mirror production conditions to ensure proper configuration and fallback behavior. For monitoring and alerting, track state transitions and their frequency to identify patterns and potential configuration issues. Monitor failure rates and success rates over time to understand service health trends. Set up alerts for prolonged open states that might indicate serious service issues requiring immediate attention. Log circuit breaker events with sufficient detail for debugging and analysis. This comprehensive approach to monitoring helps maintain system reliability and provides insights for continuous improvement. As we conclude this comprehensive guide on microservices with Go, let us review the key takeaways that will help you build robust, scalable service architectures. First, design your services with single responsibility principles and clear boundaries. Each microservice should focus on a specific business capability and maintain loose coupling with other services. This approach enables independent development, deployment, and scaling of services. Second, implement API gateway patterns for unified service entry points. The API gateway simplifies client interactions, handles cross-cutting concerns like authentication and rate limiting, and provides a single point of control for your microservices ecosystem. Third, use service discovery mechanisms for dynamic environments where service locations change frequently. Whether you choose client-side or server-side discovery, ensure your services can find and communicate with each other reliably. Finally, apply circuit breaker patterns for fault tolerance. Circuit breakers prevent cascading failures, provide graceful degradation, and give failing services time to recover. Remember that building effective microservices requires careful planning, proper tooling, and continuous monitoring. Go provides excellent support for microservices development with its performance, simplicity, and concurrency features. Combined with these architectural patterns, you can build resilient, maintainable, and scalable distributed systems. Thank you for joining this comprehensive guide on microservices with Go programming language.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.